Let us start now. Basically, yesterday, we have started the thermal stresses and went through the initials or fundamentals of the thermal stresses once again. But now, let us start from general results, which we have already told you. When the temperature distribution is known, the time of problem of thermal elasticity consists in determining the following 15 equations: 6 stress equation, 6 strain, and 3 displacement equation itself. So in order to satisfy the 15 equation throughout our body, we need 3 equilibrium equation, 3 strain equations, and 3 stress-strain relation, and the prescribed boundary condition. There are most problems, the boundary conditions belong to the use of the following 2 cases only. The traction boundary condition is that. In the case, what is traction? Traction is the force or frictional result exists in the boundary of certain surfaces. Say on road, the traction between a car wheel and the floor itself. If there is or somebody is pulling a certain weight over the ground itself, it is forcing the particular weight through against its own weight, which is like to be stable in a particular position, and you are drawing away from its position itself. These 2 are the examples mainly. The traction, what is the traction itself? Means from the boundary, what are the attracting or what are the force exist to prevent any movement or any stress at the boundary of the surface itself. That is more or less the surface traction, and it is also from surface tension itself. But we are now mostly interested in displacement boundary condition. How much the displacement takes place in the boundary with the application of due to the hitting of a particular member or due to pulling of a particular member itself. The displacement components determined should agree with the pressurized displacement of the boundary itself. Means the displacement components, whatever we may be, it should be agree with the known or displacement at the boundary itself. Means displacement cannot avoid the movement or the limitation imposed on the boundary itself, because it is you can restrict the increase or decrease in dimension by using such rectification on the boundary only and nowhere else itself. In some cases, the prescribed boundary condition may be a combination of the above 2. And there may be some traction, or there may be some obstruction in the boundary, which is not allowed to change the stress itself. Means some traction in the boundary, traction in boundary, as well as or restriction which does not allow the change in dimension. Now, the remaining method of arriving at a solution depends on the nature of the problem itself. In our books on thermoelasticity, that is temperature distribution of a body is a linear function of the rectangular Cartesian coordinate system, which means the rectangular space system like X, Y, and Z, the temperature distribution is a linear function, is directly a function of X, Y, and Z itself. It means temperature distribution depends on is a function X, Y, Z as well as the time T itself, and which is equal to alpha into time plus B into alpha into time into X plus C into time into Y plus B into time into Z itself, which means The change in time or change in time itself first. Due to the change in time, what is the reflection in x direction? What is the reflection on y and reflection of z itself? This is thus the temperature distribution with a linear function of Cartesian space, which that should not be the not depends on the cylindrical distribution, but depends on the Cartesian distribution of stress itself. Now, when t represents time, all the stress components are identically zero throughout the body. Hence, if provided all external restraints, body forces and displacement discontinuity are absent. So there is first we assume no force. Just a second. There is no restriction. No force, no body force, and any displacement, any discontinuity displacement, any discontinuity man. Conversely, under this position, there is only temperature distribution for which all stress components are identically zero. As there is no restriction, so what happens? All stress components are zero. These results are immediately obtained immediately by considering the stress commutation relation itself. Now, followed from the above statement and the linearity of the boundary value problem itself, we have already formulated through our earlier equations is 1, 4, and 5 itself, which is shown like this. One is here. Relation between the strain and stresses in all three particular direction, shear stress and shear strains, shear stress as well as shear strain, then they are they can solve the equation of sigma x by using these Lami's factors, lambda and mu itself, and same is the case with tau xy, tau z, sigma x, sigma y, and sigma z, and tau x, y, z, etc. And Lami's constants are given by this relation mu into e divided by 1 plus mu into 1 minus 2 gamma, mu is equal to g e divided by 2 plus 3 gamma. These are all already established. Next, we go for the equation of equilibrium in Cartesian coordinates. There you see, due to the effect of the stresses in x direction, the shear stress in xy plane and xy plane, and the body force z, there is no displacement itself. There is no resultant stress. The strain displacement relation is given here. Here, due to the rate of change of epsilon x is dux by dx, epsilon y dy, and is a displacement in x direction, y direction, z direction, and gamma xy is placed according to the equation itself. Next, we go. So, a linear function, what we can say, linear function, which is not quadratic but linear, is maybe added to or subtracted from a given temperature distribution without affecting the resulting stress distribution itself. The strain and displacement are altered as it is obvious. Means strains will change and displacement will observe, but stress will not change accordingly. We shall now show that if a body is subjected to uniform temperature rise, T is equal to T0 into T, means in course of time, the temperature is changing in certain period of time itself, and the boundary of the body is prevented from having any displacement itself. So what is that? There is no displacement So all the displacement in x direction, y direction, and z direction are zero. All displacements in x, y, z direction is zero. And similarly, there is no there is no strain occurs. There is no rate of change of deflection. As there is no deflection, there is no uh, shear strain, and there is no shear stress also. And only we have the stress which is induced due to this prevention of movement. And in x and y direction, all the same is equal to E into alpha divided by 1 minus 2 into V into T0, which step we have already reduced. Thus, what happens? We apply the principle of superposition, means the calculate the stresses in each section or strains in each section and just add together to get the final total strength of the your body under consideration. First, we allow the free expansion of the body due to the temperature rise. So much the strain will be created if there is no restriction, and then with no restriction itself, there is no restraint. But since all here, what we'll do, we'll take all cubical elements of the body to expand freely. So no stress developed and all elements expand in an identical manner. Thus, what we have, again, the no stress is induced in no longitudinal direction, no shear stress is induced, no deflection in strain, in shear, in torsional direction, and no strain in longitudinal direction. But strain here is equal to only the alpha into T0, the coefficient of thermal expansion multiplied by the temperature rise in course of time. And so what happens? There is a change in Ux, which is alpha T0 into x to change in x direction, the y alpha T0 y change in a y direction, and alpha z alpha T0 z change in z direction. So extensively strain exists, strain and deflection exist. Now, if we apply the boundary traction to prevent the displacement, so if the body is said to be subject to a hydrostatic state of stress, then all the elements of the body will experience the same space of stress. P is equal to P is equal to minus stress. As it is a hydrostatic stress, the stress say in the body is immersed in the water where stress is same in all direction and it is compressive in nature. That's why the stress is written as minus P itself. Stress is strain, stress is same in all direction, and compressive nature. So with this kind of stress, with this type of stresses, all sigma x, sigma y, and P, and tau xy, tau zy, is of 0. The stress is induced in x, y, and z direction, and in x, y, y, z, and z direction in all equal to 0. So the equation of equilibrium are identically satisfied accordingly. So as this happens because all this due to the action of the stress itself, the body is allowed to contract. It is not restricted to contract. So there is no stress is created in longitudinal as well as shear and torsional direction itself. Now, but strain must be there. So according to the state of stress, the strain components are F's are x, y, and z. So it's equal to 1 by E, where minus P is the epsilon x minus psi minus into minus P, which is both in z direction and z and y direction, both are equal and both are equal to minus P. Thus, the total equation becomes equation reduced to minus 1 by 1 plus 2 into psi into P itself, where torsional strains, strain is equal to 0 itself. Only the strain in the longitudinal direction is existing. Therefore, Ux is equal to 1 minus 1 by x into 1 minus 2 into gamma into P into x. Because if in the x direction or in the x length, if we know the strain, you can know the displacement, which is equal to Ux itself, because multiplying the strain with the original length, say x itself. Similarly, Uy is achieved by multiplying the strain in y direction by y, and Uz is achieved by multiplying strain direction into z. So in the original problem, above value of Ux, Uy, and Uz together with the values of Ux, Uy, and Uz already produced here due to the change in temperature, we can use both of them together, which is Ux change in displacement due to change in temperature, and change in displacement due to effect of the external force P, where there is no restriction takes place. Only so, but no stress is induced, but strains in longitudinal direction is induced. So what we are doing, the difference between this strain in thermal strain as well as strain due to the pressure P is supposed to be equal to 0, because in order there no residual strain is possible here, because due to the maintenance of equilibrium condition itself. So strain in thermal strain, say N is equal to the strain due to longitudinal displacement. We are using displacement, not the strain, because we are multiplying the strain with means of the original length itself. Thus, from this two equation, we get the value which is permissible value of the external pressure P, which is given by E into alpha here by 2, 1 minus 2 into mu into P0 itself. So here we know sigma x, sigma y, and sigma stress induced is equal to P only, and is equal to minus P. That is the only the external stress applied, and that is equal to E into alpha minus 1 minus 2 into mu into T. Now let us go for the thin cylindrical disc. Temperature is symmetrical about the center itself. So consider a thin disk subjected to a temperature distribution which varies with R and independent of theta. We are considering cylindrical coordinates here, that is only R and theta itself. Now, our assumption is that temperature is parallel along with the radially, only radially, when from radius R at the center where R is equal to 0, radius equal to R, there is a variation in temperature itself, and so the effect of variation, the strain and displacement also takes place in R direction, and there is no this temperature variation is totally independent of theta. Means if there is any induced angle over the surface, and they are formed like this, there is no displacement due to the temperature effect to the circumferential direction itself. No strain or displacement in circumferential direction. Stresses or displacement does not vary over thickness. Again, this is assumed. It is not vary over the thickness, because thickness is small, as sigma R and sigma theta. the stress along r direction, stress along the circumferential direction, there's my direction, they should supposed to satisfy the equilibrium equation for the string condition. This is the equilibrium equation given by d sigma r by dr plus sigma r minus sigma theta divided by r itself equal to 0. Thus, body force here are neglected here. Also, because of the symmetry itself, tau r theta means stress in r theta plane and working along the length longitudinal direction is equal to 0. Right? Sigma z, which is the stress along longitudinal direction, is equal to 0. Then the stress strain relation will become sigma r in terms of polar coordinates from the equation 9.a, which is this is given in Cartesian coordinate x, given in Cartesian coordinate x, y, and z. Now in polar coordinates, it is not available in z direction or longitudinal direction. Only we replace ex by er and ex ey by a theta itself. Means strain along radial direction as well as circumferential direction and no strain along longitudinal direction. Thus, so what we get here in polar coordinates, we put with epsilon r in case of x and sigma r minus mu sigma theta plus r into alpha into t, then epsilon r plus 1 by e into secta theta into mu sigma r plus r into t itself. Solving the above equation for r and theta, if we solve it for sigma r and sigma theta, we'll get sigma r and sigma theta in an equation like this in terms of epsilon strain in radial direction, epsilon theta strain in circumferential direction, coefficient of thermal expansion, as well as the change in rise in temperature due to course of time itself. Then, in case of circumferential stress, radial stress, it is radial stress, circumferential stress. So sigma r is equal to e by gamma square, 1 minus gamma square, epsilon theta plus mu into mr plus minus 1 minus mu into alpha into t itself. Is the same except that theta and r changes position itself. Now, in the equation of equilibrium, we have already reduced here. This is the equation of equilibrium, d sigma r by dr, d sigma r minus d theta by r. So if we replace this equation, and what will happen, and make certain simplification, sample certain simplification, we will find that this dr by mu sigma theta is under the derivative d by dr multiplied by r, and this two portion here is sigma. If we put sigma and sigma theta here, this direction, and we'll have they cancel each other, and this portion with 1 minus mu into epsilon and epsilon theta is remains here. Means epsilon r minus epsilon theta into 1 minus mu is available. This will be equal to 1 plus mu into alpha r into delta t divided by delta r itself. So this portion will be under derivative. It will be after differentiation, we'll take this particular form itself. Now, and it put it on the right side of the equation equal to sign to make our calculation a bit convenient. Then strain displacement relation for a symmetrical strain body, you know, epsilon r, the rate of change of the displacement in radial direction divided by r, and epsilon theta is equal to rate of it is the radial displacement divided by the full radius itself. Radial displacement divided by radius. Now, so substituting this value of f star r and f star theta in this equation, f star theta will be u by r and f star r will be du by dr theta. So here we have a differential equation of second degree. Then d square u r divided by dr square plus 1 by r du r minus u divided by r square into multiplied by 1 plus gamma into alpha into d into t divided by tr itself. So it can be written as with after further simplification, we can make d by dr outside the bracket, which is, and inside the bracket is 1 by r into d by dr r dr. So if we take the derivative again, this will take this particular position and particular position here, and 1 minus gamma mu r, it remains as it is itself. Full position, this will be like this. Now, if we integrate the above the equation, what will happen? We have this equation remains same. Integration above the equation becomes u r itself 1 minus gamma into alpha 1 by r integration of 0 to r t into r into dr plus c1 into r and plus c2 divided by r itself. So what we are left with, the displacement in radial direction itself. That is displacement in radial direction itself. Now it is also the above equation. This is actually where t is put equal to 0. Our ideal solution here for the polar coordinates, this displacement equation becomes if t is equal to 0. Now, the lower limit a of the integral above depends on the discrete scale. For this, if there exists a hole, a is the inner hole, and for a solid disk, a is equal to 0. So we have to depend on the boundary condition itself. Depends on the boundary condition to solve C1 and C2. Now, so lower limit of the integration can be a here, which is given here, where a is the if there is a hole, and a is the radius of the hole itself. And for a solid disk, a is equal to 0. Then in that for a solid disk, we have to integrate from 0 to r itself. Now, the stress component is determined by substituting value of PR. In we have to put this value in the stress component sigma r and sigma theta. Equation 13 is using 13. We have to substitute the value of QR, which is given here, here and here, and using the result in equation 11 also, what is given here, what is the value of sigma r and sigma theta itself, then the results will take this particular form of sigma for sigma r, and this is a particular form of sigma theta, which contains the integration from a to r dr dr. Here a is the inner radius, r is the radius under our consideration, and both C1 and C2 constants are all exist, and that is also the radial distance r square is also given here. Similarly, for sigma theta is more or less equation is the same, only the signs of the change, except one alpha et portion is comes into play, plus 1 by v square C1 C2 plus 1 by v square C1. Only dimensions are changes accordingly. This is plus is replaced by minus, and minus is replaced by plus itself. and we have new function all ET. Now, constant C1 and C2 are determined by the boundary condition itself. We have to know the boundary condition. We shall know two specific boundary conditions which should be observed by a linear variation of temperature with R will also increase stresses. If temperature changes with the radius, stress is also induced. What do you mean by that? It does not contradict the statement in earlier section that stresses in a body are zero if the temperature distribution with respect to the Cartesian frame of reference and if the body is free from thermal restriction for body reference. Which this means what they mean is there may be strain in there strain may not exist in Cartesian direction in that is in x and y and z direction. So no stress is induced in this Cartesian direction. No stress is induced in x, y, and z direction itself. But strain may exist in radial direction. Just 1 second. Hello. বারোটা কুড়ি আচ্ছা আমি ক্লাসটা করে যাচ্ছি and strain may exist in radial as well as and circumferential okay. Now what happens? A linear radial variation will not give a linear variation with respect to x, y, z axis itself. So radial variation will not create a radial variation in x, y, and z direction. So T change in thermal change in temperature which is equal to K into R. The K into R is equal to square root of x square plus y square plus r z square. Now, if we consider a solid disk of solid disk where A is equal to 0, means there is no internal hole and A is equal to 0 itself. And it is observed from L'Hospital's rules that limit of R tends to 0, 1 by R equal limit of between 0 to R is T into R into TR is supposed to be equal to 0 itself. Means all these variations here in the same hence the Cartesian coordinate C2 should be equal to 0 itself. Why? If this exists here and here, this situation exists here and here. If C2 is not equal to 0, this is equal to 0 here, C2 is equal to 0 here. If C2 is not equal to 0, then when R tends to 0, this both these stresses tends to infinity itself. Now, both these stresses tends to infinity itself. Now, the remaining, so remaining constant C1 is determined from the condition that sigma r equal to 0 at sigma r is equal to P. Hence, outer radius of the disk, there is no stress existing. All the stress is created from inner to outer radius and not at the outer or inner radius itself. Those equation, this equation will reduce, therefore C1 will be given as 1 minus gamma A by B 0 to R T into R dr. If we substitute in this equation, in the above equation, then this equation for sigma r will take the form of alpha into E within bracket 1 by B square is here, where here R is replaced by B and T into R dr. This integration itself minus, this is 1 minus gamma into C1. Let's see, then 1 minus gamma into 1 plus gamma, the 1 minus gamma square into y a by b square into t equal to 0 to tr into 0 itself. Same is the case with sigma theta. Now, at L'Hospital's rule, sigma r is equal to, at L'Hospital's rule, sigma r is equal to limit tends to r square, etc., which we can write down as half average of the change in temperature equal to T0 by 2 itself. Now T0 is the temperature at the center of the disk itself. So at R is equal to 0, sigma theta both are equal to 0, and is equal to R is equal to 0, both sigma r and sigma theta is equal to alpha into E 1 by B square 0 to R TR into E, and we replace at the value R is equal to 0 here. We are replacing this term here and this term here is by half T0 itself. Next, let us consider this with a hole of radius A. Say, now we are thinking of a hollow disk itself. Now, with this type of this sigma r is equal to 0, and where r is equal to A and r is equal to B, both at inner radius of the hole and the radius of the outer side, both are equal to 0. So C1 is equal to 1 plus gamma minus C2 is equal to 1 minus gamma divided by 1 by A square is equal to 0. So if we put this value in the equation itself, if we put the value of say 9.15, as in case of in the 15 here, where sigma r is equal to 0 at A and B, and so we get the equation between C1 and C2, 1 plus gamma minus C2 into 1 minus gamma into 1 by S square is equal to 0. Now, and the equation will take this particular form minus alpha and put C1 and C2 like this, solving we get C1 is equal to, first equation will take this particular form in 9.1. This equation will take this particular form by putting A and B itself, and this equation will take this particular form here, and it will reduce to these two formation itself, this one and this one. If after solving them, we get C1 is alpha into 1 minus gamma divided by 1 by B square minus C square into A to B TR into DR. C2 is minus alpha is equal to 1 minus gamma into A square, B square minus A square into 0 to B T into R dr. And substituting equation 15 and 16 here, will have sigma r with this function and sigma theta with this function, and from equation r, equation or displacement in radial direction is given as A by R. Radius equation is alpha by R 1 minus gamma into 0 to R T into R into dr itself. Thus, if the temperature is constant, then all these space constant components are 0, and radial displacement is UR into alpha RT itself. So, what we are having here, first of all, we have worked here. What is the thin circular disk? And initially we have assumed there is an important assumption. There's that there may not be any change in the stresses and displacement in x, y, and z direction, and as well as there no stress is induced there, but radial and circumferential direction there exists stress and strain. Now, next we have the thin circular cylinder, which is we've gone through the thin circular cylinder case, where first of all it don't have the hole, and next one is this at the hole itself. Next we use the equilibrium condition itself. Equilibrium equation is one, where in which is for cylindrical coordinate system is equal to d into sigma by r, sigma minus sigma theta by r itself. As we know, the stress in r direction and theta direction is possible, as well as displacement in r direction, that is u_r, both is possible by keeping the displacement in x and y and z direction is equal to 0, and both sigma and ux, sigma x and ux are equal to 0 itself. Now, or they are equal to each other. But body force here, like gravitation and the surface tension, etc., they are ignored, and thus also become a symmetry itself. Now